Okay, today we are going to be doing some more applications of exponential growth and decay. Remember to take really good notes because, of course, it will help you with your learning and understanding, and also because you have your notes lesson quiz that we'll do during class, and you want to make sure you have what you need to do well on that quiz. Now, what you see on the first slide here, you do not need to write down. This is just a reminder of the exponential growth and decay models that we did at the beginning of the chapter when we were doing other word problems. So, for example, we used the equation y equals a times 1 plus r to the t for exponential growth. And an example of that is find the final hourly wage if a $13 starting wage is increased 4% each year for 10 years. And so what we did with that information was we put it into the model where A is the starting wage, so 13 goes in for A, and then R is the increasing rate of 4% converted to a decimal, so 1 plus 0.04. We could write that as 1.04, and then that's to the T, so there's our model. And then from there, of course, we could plug in 10 for T and get the answer. If I want to simplify my model, I would just write it like this. Here we see an exponential function with a base that's greater than 1, and of course greater than 1 bases imply growth. Okay, and then we also looked at some models with exponential decay, where instead of a 1 plus r, we have a 1 minus r. And an example of that is this statement here. A vehicle purchased for $20,000 depreciates at a constant rate of 12%. Determine the approximate value of the vehicle 6 years after purchase. So to make that model, we would put the initial value of the vehicle as A, 20,000. And then for 1 minus r, we have 1 minus 0.12 for 12% raised to the t. And that model would look like y equals 20,000 times 0.88 to the t. And the base being 0.88, a number less than 1, implies decay. And then we would use that model to solve the problem by putting 6 in for time. So that's just a reminder of what we've done before. And what we're going to do today, more growth and decay applications that all use the following model, y equals y naught e to the kt. So go ahead and start your notes now. My plan is just to have one long video today rather than a series of videos. And after describing the parts of this equation, we'll go ahead and work through 3 examples. So figure out what notes number you're on, and you can copy down this equation, and then we'll talk about what the parts are. So just like the previous equations we were looking at, you have a final amount, y. So that would be the final amount of whatever you're working with, some substance or some population. You can also call that the amount at time t. Y naught, that is our initial amount. In the previous equation, we used A for that, but right now we're just calling it Y naught because, hey, why not? Y naught is this Y sub 0. Naught is N-A-U-G-H-T, which basically means nothing. So when I say Y naught, I mean the Y value at time 0. That's the initial amount. At time 0. T is time, and the units of time can vary from problem to problem. Seconds, minutes, hours, years, days, doesn't matter, anything. When we did compound interest, it was always years, but this time it could be different units of time. And K is the growth or decay constant. If K is a positive number, it will be growth. If K is a negative number, it will be decay. Okay, so let's go ahead and work through our examples, and remember, be sure to write down the problems as well as working through the steps to solve them so that your notes are thorough and useful and so that you're prepared for the quiz. Number 1, the projected world population in billions of people t years after the year 2000 is given by the function f of t equals 6.079 e to the 0.0126t. According to the model, in what year will the population reach 10 billion? So let's dissect this a little bit. We have our model y equals y naught e to the kt. So y naught is the initial amount, and that number here is 6.079. So 6.079 is the initial population at time 0. And what is time 0? According to the problem, that's how many years it's been since the year 2000. So that would be the year 2000. So 6.079 billion was the population of the world in the year 2000. What else do we have here in the equation? We have this number 0.0126, and that is in the place of k. So k is 0.0126. That's the growth constant, and because it's positive, we are talking about growth. And what we're doing in this problem is we're finding the final amount, we're finding the time to reach a final amount of 10 billion. So let's plug in 10 for 10 billion in for the final amount, f of t, and we're going to solve for t, time. Okay, so yesterday we solved equations like this where we had to solve for the variable and the exponent. So we're solving an exponential equation, and when you're solving an exponential equation, you use logarithms. We're not ready for logarithms until we have divided both sides by 6.079 because we have to get the exponential part by itself. Now what I would do is I would just leave the fraction here as it is. I would not worry about simplifying that or plugging it in the calculator. It doesn't look pretty, but we'll just leave it like that for now. Now we're ready to take the log of both sides, and since we're using the natural base e, let's take the natural log of both sides. Natural log of the left. And what's going to happen when we take the natural log of the right is that it will cancel with the e, leaving us with just 0.0126t. Okay, so the last thing there is to do is divide both sides by 0.0126 to get t by itself. So we have natural log of 10 divided by 6.079 over 0.0126. Now, I would not use the calculator until this point. You don't want to use the calculator, approximate, and then do more with it, and approximate, and then potentially do more with it. That's just going to throw your answer off a bit. So just wait until this point, and now you put it in the calculator, and you get approximately 39.5. That would be the number of years after the year 2000 when it reaches 10 billion, the population reaches 10 billion. So let's call that the year 2039. So in the year 2039, the population will reach 10 billion. I wonder if that will really happen. Will it happen sooner? Or will it never happen? I don't know. Do we have the resources to sustain 10 billion people? What's the population now? So many questions. Okay, let's move on to the next example. Problem number 2. A certain bacteria population grows according to the model y equals y naught e to the kt. At time 0, there were 2 million bacteria, and at time 5, there were 12 million bacteria. Find the amount of time it takes for the bacteria population to double. You can't necessarily tell when you read the problem, but this is really a two-part problem. In order to find the time it takes for the bacteria population to double, we need to know the value of K. We don't yet know the value of K, so we have to find it. So the first part of the problem is find K. Once that's done and you plug that into the model, then you can actually solve the problem. And the way you find K is you use the given information. So we know that if we started with 2 million bacteria and ended with 12 million bacteria, that would take 5 units of time. I don't think we're told here what the unit of time is, so just 5 units of time. So I'm going to plug those numbers in. 12 for 12 million is the final amount. 2 for 2 million is the initial amount. And then we have e to the k is still k. We're trying to figure that out. And the time that has elapsed is 5, so e to the 5k. Let's solve this equation for k. Divide both sides by 2. Take the natural log of both sides. And divide both sides by 5. All right. Now that is the exact value of k. I would leave it like that, or if I'm going to put it in my calculator, I'm going to store it so that I don't have to round and use a rounded number, which will throw off my accuracy. So let me just teach you how to store. So grab your calculator. Okay, so I need to type in natural log of 6 over 5. And press enter. That's the number we want to store. So notice next to the 1 button, you have a stow button. That means store, so press that. And then you need to choose a letter for storing this number, giving it a name. So I would choose K in this case. So you're going to press alpha, and then you're going to find the K. They're in alphabetical order, so here's the K right above the parentheses. And then you press enter. It repeats the number telling you what it just stored. So if I needed to use that number to do other things with it, for example, let's say I was going to multiply it by 2, I would just type 2 and then alpha K, enter, and there's the number, or whatever else you're going to do with it. So we'll come back to that in a minute. Okay, so if you feel like it, you could write down the approximate value of K. It was approximately 0.358. But make sure you don't use that rounded off number. We're going to use the stored number or the exact number. Okay, so we did part 1, which is to find K, and now we can go back and solve the problem. Find the amount of time it takes for the bacteria population to double. So if it's going to double, maybe it's going from 2 million to 4 million, or is it going from 12 million to 24 million? Is it going from 1 million to 2 million? We could choose any of those. It's not going to matter as long as you're doubling. It's all going to work out the same. So suppose I decide that it's going from 1 million to 2 million. So the final amount is 2 million. That goes in for Y. The initial amount is 1 million. That goes in for Y naught. And then we have E. And then we have our K value. Now I'm going to writing that natural log 6 over 5 number in here by just writing it as K. We know K. Eventually we're going to use K. I'm just going to call it K for the time being. And we're solving for the time. Find the amount of time it takes. Okay, divide both sides of the equation by 1. Take the natural log of both sides. And we're solving for time, so we need to divide both sides of the equation by K. All right, now if I'm giving an exact answer, it's time for me to plug my exact value of K back in here. So that's going to look like natural log of 2 divided by a fraction, natural log of 6 over 5. And you know that dividing by a fraction is the same as multiplying by its reciprocal. So I could write that as multiplying by the reciprocal of the bottom, we're going to have the 5 on the top, multiplied by the natural log 2 that's already there, and divided by the natural log 6. Because dividing by natural log 6 over 5 is the same as multiplying by its reciprocal. So that would be the exact time for the population of bacteria to double. And if you're wanting the approximate time, which kind of makes sense in this context, like you kind of want to know how much time that is, that number that we're staring at right now doesn't really tell us much. We can go back to the calculator. Let's use our stored number. So this was natural log of 2 divided by k. 1.93 units of time, whatever they were. If you didn't store the number, then you can just type in our exact answer, which was 5 times natural log of 2 divided by natural log of 6. Either way, you get the same thing. 1.93 units of time. Okay, T is approximately 1.93 units of time for the bacteria population to double. Whether it's going from 1 million to 2 million, 12 million to 24 million, whatever it is, it's going to take the same amount of time to double with these growth constraints. Okay, let's take a look at the third example. A certain radioactive substance decays according to the model y equals y naught e to the kt. There were initially 800 grams of substance present, and 2.5 years later there were 400 grams. How much of the substance will be present after 4 years? In other words, 4 years after the initial time. Okay, so this is similar to the previous problem. It's a two-part problem. We have to first find K, and then we have to answer the question, solve the problem. So to find K, just like we did in problem number 2, we're going to plug in the numbers that we know. We know it started with 800 grams of substance, and then later there were 400 grams, so 400 is the final amount. 800 is the initial amount, and we know that took 2.5 years, so time, T, is 2.5, and we don't know K. So we're plugging in all those numbers and we're going to solve for K. By the way, do you notice that it went from 800 grams to 400 grams, which means half the amount, and it took 2.5 years. So what is that? What is the phrase we use to stand for the time it takes to decay to half the amount? That would be known as the half-life. So for this radioactive substance, the half-life is 2.5 years. Whether or not we need to call that the half-life for this problem, I don't know, but in a future problem, if you are asked about half-life, you need to know that that is the time it takes to decay to half the starting amount. Okay, let's keep going. We're going to divide both sides by 800, and that gives us 1/2 equals e to the 2.5k. Take the natural log of both sides, and then divide both sides by 2.5. And that is our K. That is our exact K. We need that exact number to do the second part of the problem. But again, if you want to store that in your calculator and then use the stored number later, that's fine. Okay, now it says how much of the substance will be present after 4 years. So we're given the time, and we need to find the final amount. So the final amount is the unknown. The initial amount, are we supposed to use the 800 or the 400? Let's see, it's 4 years after the initial time. Initially they were 800. We're supposed to use the 800. You have to read the problem really carefully there. And then it's times e to the, remember the k, I'm just going to call it k again so I don't have to write that fraction with a fraction in it inside an exponent. That's just kind of messy and hard to do. And then we have the number 4 for our time. Okay, so we could put this whole thing in the calculator. I'm going to go ahead and store my K and then type this whole thing into the calculator. So if we put the K in there, we had natural log of 1/2 divided by 2.5. Notice that that is a negative k, and a negative k means what? A negative k means decay, so that makes sense for this problem. Okay, let's store that. So we press store, alpha, k, enter. And now what we're going to do is 800 times e to the k times 4. Notice that the way my calculator works is that the k and the 4 are both in the exponent, but if you have a different calculator, you might need to put parentheses around your k times 4 just to make sure that they're both in the exponent. And we get 263.9, depending on how you want to round, to 63.90 if you're rounding to the nearest hundredth. For our answer, how much of the substance will be present after 4 years. So y is approximately 263.90. And what kind of units are we looking at here? Looks like grams. Okay. Now, before we leave this problem, we could think about the reasonableness of our answer because of the whole half-life idea. So we know it takes 2.5 years for this substance to decay to half the amount. It went from 800 grams to 400 grams in 2.5 hours. So it's going to go from 400 grams to 200 grams in another 2.5 hours. That would be 5 hours altogether. So what would it do in 4 hours? Well, it wouldn't quite make it to another halving, however you want to say that. It wouldn't quite make it to 200 because we haven't had the full 5 hours yet. So in 4 hours, look at that, it's a little bit above 200. That kind of makes sense, in my opinion. Okay, there we go. We made it through 3 examples of exponential growth and decay using y equals y naught e to the kt as our model. And when we go to class next time, we're going to do a few more of these examples together just to make sure everybody gets it and to make sure everybody's using the calculator properly. And then we'll be able to do some practice problems. Thanks, everybody.